if we have molecules that have p orbitals involved, we have to use a slightly modified looking diagram for our molecular orbitals. And those two diagrams are shown here. Basically, without going into why or how the diagrams look the way they do, what we need to know is that for oxygen, fluorine, and neon, we would want to use this diagram. And you'll see the difference is the placement of the pi orbitals here and the sigma here. Those are inverted over here for boron, carbon, and nitrogen. So if we were doing O2, for example, like we will in the next slide, we are going to use this diagram here. If we were doing carbon, nitrogen, boron, be this diagram on the right. So for oxygen, we have each one is going to be a 1s2, 2s2, 2p4 electron configuration. So that gives us 2 electrons in the s orbital on each side, and it gives us 4 electrons in the p orbital on each side. So I'll place those in the appropriate orbitals there. And now we've got a total of 6 electrons to place into the p orbitals. So to start, we'll start with the lowest energy level, which is going to be the 2s. And the 1s is not important because it is below the valence shell, so it's not involved in bonding. So we're only going to consider electrons in the valence energy level. So in this case, we've got 4 electrons. We're going to place those into the appropriate molecular orbitals here. And you can see that the sigma, sigma star are filled. Now, we go up to the next section. We've got a total of 8 to place in those energy levels. So we will start by placing 1, 2 there. And then we'll go 1, 2, 3, 4. So we have a total of 6 now that have been placed. And Hund's rule says that we have to, when we have degenerate orbitals, we have to place an electron in each orbital before we can pair up any of the electrons. And so that means that when we get to the pi stars, we're going to have to place 1 electron in each of the 2 pi star orbitals before we would pair up any of them. And so in this case, we only have 8 electrons total in the upper section. So that leaves us with these 2 electrons right here that are unpaired. And so that tells us a couple of things. Number one, we can calculate the bond order for the molecule. And so the bond order in this case is going to be the number of bonding electrons. So it's going to be 2, 4, 6, 8. So it's going to be 8 minus the number of antibonding electrons, which are going to be 2, 3, 4. So 8 minus 4 divided by 2. And the bond order for this one is 2. And that's actually consistent with the Lewis structure, which we know is showing a double bond. And so there's 2 things that we can learn from this. Number one, we can learn the bond order, and that is the bond order is 2. And the second thing we can learn is whether it'll stick to a magnet or not. And you can see here that it will, based on the fact that it has these unpaired electrons in the pi star antibonding orbitals. So what if we have a heteronuclear diatomic molecule, that is, one that's not O2 or N2 or C2, like, for example, carbon monoxide, CO? This poses a couple of interesting questions. Number one, which of the 2 molecular orbital diagrams do you use? Do you use the one for carbon, or do you use the one for oxygen? And so the answer is you use the one for the more electronegative atom. So in this case, oxygen. So we'll use the one for oxygen. The other thing that it does is it slightly skews the energy values, where the more electronegative atom tends to be a little bit lower in energy than the less electronegative atom. So on the right-hand side here, we're going to have carbon and, oxygen. And on the left-hand side, we're going to have carbon. So we are going to place electrons in those energy levels now. And so for carbon, we're going to have a total of 2 s electrons and 2 p electrons. For oxygen, we're going to have 2 s electrons and we're going to have 4 p electrons. So that gives us a total of 2, 4, 6, 8, 10 electrons to deal with. So we're going to go ahead and start putting them into the molecular orbitals, and we're going to do that by placing 1, 2 until the energy levels are full, and we'll work our way up here. And so we've got, that's 5, 6, 7, 8, 9, 10. So this one's finished. Now, again, we can calculate things like bond order. We can calculate, well, we can't calculate, but we can determine based on the presence of paired or unpaired electrons, we can determine whether or not carbon monoxide will stick to a magnet. So since there are no unpaired electrons, we can assume carbon monoxide does not stick to a magnet in this case. So that's pretty much it for molecular orbitals. We don't go into any more than 3 atoms. The molecular orbital diagram gets pretty complicated after just 2 atoms. So everything you're going to see is going to be 2 atoms or less, and you're going to look at homonuclear or heteronuclear diatomic molecules. And so once you know how to do those, then you'll be good to go.